Let's talk about some inverse functions. What we're going to do is we're going to suppose f and g, that's f of x and g of x, are inverse functions of one another. So if f and g are inverse functions, in fact, let's write this down. If f and g are then, well, let's talk about what we know about inverse functions. Inverse functions, graphically, the x's and y are switched. So if we compose a new function with f and g, so I'll put that as the then. If we make an f of g of x, well, if f and g are inverse functions, then whatever f does, g undoes it, and we come right back to x. They undo each other. Well, and then, so of course, g of f of x, g would undo f, and of course we're back to x. So both of those cases are true. Now, we might use notation to talk about an inverse function, such as this right here. We could say that, let's use this notation for the inverse. So g is the inverse of f. I could use that one, for example. And then in which case, I'll notice that f composed of its inverse is back to x, and then f inverse of the function is back to x in both cases. So this is just a notation for the inverse. It's not an exponent of -1. It's a symbol, that superscript symbol, to talk about the inverse, like that. All right, well, we didn't talk about, the derivative of an inverse function yet. And of course what we could do is, if we're given a function, we could find the inverse if we're able to. But what we're going to do today, we're going to use something that you know really well, the chain rule and the power rule. So what I'm going to do is I'll just write now, and I'm going to write this f of g of x again, like this, just from up here. And I'm going to take the derivative of this composite. So I'll use some Leibniz notation, like so, that says give me the derivative with respect to x of f composed of g of x. Well, here comes our chain rule. And I know you know this one well, so just think about it for a moment. And of course it's f prime composed of g times g prime. And I'll just put by the chain rule. There we go. So by the chain rule, we know this is true. I'll make another note, and so what I'm going to do is I'm going to take the x right here. I'm going to take the derivative of x with respect to x. Here's our power rule. It's x to the 1 power. The 1 comes down, right? X to the 0, which is 1. So I got a 1 by the power rule. Like that. So let's bring it all together. And it's going to look like this. So I have f composed of g of x is equal to x. And I write that down, and I take the derivative of both sides of this equation. Of course, I know what those are by the chain rule and power rule. So I have f prime composed of g times g prime equals 1, like this. Now, of course, we know that g is the inverse function. What I'm going to do is I'm going to solve this equation for this g prime, because then I have the inverse, the derivative of the inverse, and I've got a quick little easy formula for this one. So let's go ahead and do that. We'll solve this one for g prime of x, and we get 1 over f prime of g of x. like so, which is kind of fun. What I'm going to do though is I'm going to take this notation from up above here and replace the g with this inverse notation. So there's g, and I'll use the little prime symbol, Lagrange notation. And the independent variable here is x, but we might look in our textbook, it might have an a or some other statement there. Now over on this side, I have my f prime, and here I have g, which is this inverse. Like so. Oh, I'm off the page just a little bit. Put a little highlight around it. And we have a quick, easy formula to use if we wish to find the derivative of an inverse function, and we don't even have to go find it, which is pretty awesome. Well, let's try an example with our new formula to see how it works out for us. So I'm going to take our little formula for our derivative of an inverse function. There we go. And I'm going to look at this example right here. F of x is x cubed plus 2x minus 1, and we're looking for the inverse. But you don't even have to go find it, because we know, in fact, it maybe would be a kind of a tricky one, right? So what I'll do is I'll use this formula, and in place of x I'll put a 2. And so I'm going to know that this will equal, now I'm just following along with my formula that I have written in red right here, 1 over f prime of the inverse of, there we go, like that. So it looks like what I'm going to need to find then is, if I'm going to use this, I need to know then what value do I plug in for x I get out at 2, right? Because this part right here that I'm looking at, unless I want to go find the inverse, I'll be stuck with trying to figure this one out. And so one way we can do this that makes it kind of easy is if we grab our calculator and put the function in here, we can go to the table. Now just a little note, I like to set my table so the independent variable is on ask. So when I go to the table, I can plug in anything I want like this. So I go to the table, and what I want is I want to put an x in here so a 2 comes out. Right? So it's like 0, I get a negative 1. I knew I would. And plug a 1 in there, I get a 2. We found it. It's x equals 1. But put a 2 in, a 3 in, a 4. You can see this function's increasing. We knew it was when we saw the graph, right? So the table here tells us that this part that I highlighted right here, remember what an inverse function does? It swaps the x and the y, right? So when y is 2, it meant that x is 1. Right here is that swapping that we know. So this is all equal to 1. So I'll just write this below here. I need to find 1 over f prime of 1, like this. And I'll just highlight this again because we know that by inspection, the inverse function, when evaluated at 2, will equal 1 because f of 1 is equal to 2. I'll just say, hey, remember that, right? Now, we didn't go find the inverse function. We just figured that out, what x causes that one to occur. But anyway, we're almost ready to go because all we need now is the derivative, which I think we can handle that one. I'll use this Lagrange notation, f prime. I like to make it a little bit slanted so I don't confuse it with a 1 and confuse it with an inverse notation, a negative 1, right? 3x squared plus 2. And I'm going to plug in a 1. F prime of 1 is 3 plus 2. That's a 5. And so all this is 1 over 5, which is our answer we were looking for all along. That's what this is right here. Well, we might want to summarize that nice and neat, saying that the inverse function's derivative evaluated at 2 is 1/5. I want to show you one other thing, though, because remember, inverse functions swap x and y, right? They swap x and y. That's what inverse functions do. So since I already had this thing graphed nice and neatly, I want to show you something that's kind of fun. Second calc dy dx. Let's plug in a value, x equals 1, and you get the derivative at 1 is equal to 5. A little rounding error here. We found that here. Now what we know then, because the x's and y's are swapped when we have the inverse function, if I were to find the inverse function and graph it, it'd have a reflection through the y equals x line right here. And so I know then that dy dx, when x's and y's are switched, I have dx dy, and it'll be 1/5 instead of 5. So we actually knew all along, once we found this, that our derivative would be 1/5. Once we find that dy dx is 5, we'll know that 1 over that will be the 1/5. Let's just make a note of our observation that we're just talking about, and that is graphs of inverse functions have reciprocal slopes. So I'm going to write that down. All right, well, let's take a look at it. I graphed that function, of course, and I made a quick little printout of it so we could kind of explore this inverse function. Now I'm just going to draw it. I'm not going to find explicitly what the function is in terms of x's. I have my function graphed here, and I've brought some just some transparent paper with, this is kind of fun stuff because we can find our y-axes and our x-axes, right? These are x-axes and our y-axes, and we can trace the function right through here like this, and then just say that's f. Now, because the inverse function swaps x and y, I need to make sure that this is my positive y direction, this is the negative y direction, this is the positive x direction, this is the negative x direction. So when I swap x and y, I want to be careful that I swap them the right way, right? Now, there we go. Looks like this. I don't have the neatest picture in the world, but what I do then is I just trace through again like this. There we go. And now I've got the graph of my function and its inverse, like so. So now I'm going to do my best to show at some point then, at some point, wherever that might be, there would be a slope, and that slope would be that slope of the tangent line, which we might say the slope of that tangent line would be dy dx, right? So it looks like it's over here as we swap the x and the y. And then the derivative here, like this, since x's and y's are swapped, that slope would be 1 over dy dx. This is a fun little picture to help keep that in mind. All right, let's wrap it up.